Okay, first, we will talk about the objective of the California bearing ratio. Okay, the objective of the California bearing ratio is to determine the California bearing ratio (CBR) value of the subgrade soil. Okay, next we will go to the theory about the CBR test, California bearing ratio. The California bearing ratio (CBR) test is used to measure the strength of soil for road construction. The soil is compacted and tested using a metal plugger. The test checks how much force is needed to penetrate the soil at depth of 2.5 mm and 5.0 mm. The CBR value is the percentage of the applied load compared to a standard load. Okay, this is the table that we get from the rubric. If the CBR value at 2.5 mm is higher than at 5 mm, use the 2.5 mm value. If 5 mm is higher, repeat the test. If the result is the same, use the higher value that we get. Okay, next for the apparatus. First, we are using cylindrical mold with inside diameter 150 millimeter and height 175 millimeter. Provide with a detachable extension collar 50 millimeter height and a detachable perforate base plate 10 millimeter thickness. The second item is spacer disc 148 millimeter in diameter and 47.7 millimeter in height along with handle. For the third one is metal rammer, weight 4.89 kilogram, a drop 450 millimeter. Number 4 is weight 1 annular metal weight and several slot weight within 2.5 kilometer each, 147 millimeter in diameter with a central hole 53 millimeter in diameter. For the number 5 is loading machine with a capacity of at least 5,000 kilogram and equipped with a movable head or base that travel at a uniform rate of 1.25 millimeter per minute, complete with load indicating device. Number 6 is metal penetration piston 50 millimeter diameter and minimum of 100 millimeter in length. Number 7 is two dial gauge reading to 0.01 millimeter, and the last one is 20 millimeter IS sieve.
So I want to tell you about procedure of California bearing ratio. First is sieve the sample through 2 mm as sieve. Second is take 5 kg of the sample of soil specimen and add water to the soil in the quantity such that optimal moisture content or field moisture content is reached. Third is the soil and water are mixed thoroughly. For space, this is placed over the base plate at the bottom of mold and a coarse filter paper in place over the space dish. Okay, so for next procedure is 5. Mix the soil with water and divide the mold into 5 equal parts. 6 is fill 1 part with soil and compare as using 56 below ODA 4.89 kg hammer and repeat for all 5 layer. For 7, strike off excess soil. Remove the collar and invert the mold and remove the base plate. For 8, add a surface weight of 2.5 kg on top soil and place the mold on the testing machine. Okay, for the next last procedure is 9. Bring the plunger in contact with the soil and apply a setting load of 5 kilograms. For 10 is set the dwell just reading to 0 and apply load data constant rate of 1.25 mm or per minute. 11 is record the load at 0.5, 1.0, 1.5, 2.0, 2.5, 3.0, 4.0, 5.0, 7.0 and 10 mm penetration. For last step is plot load versus penetration graph and calculate the CBR value at 2.5 mm and 5.0 mm penetration. That's all.
Okay, now let's look on for the data. Okay, the first one is the weight of primer used was 4.89 kilograms and 56 blows were applied during compaction. The surcharge applied by the plunger was 50 millimeters with a cross-sectional area of 19.83 square centimeters. And on the right table, we can see the moisture content data. The empty container weighed 150 grams, and with the moist sample, which is 450 grams, after oven drying, the total was 420 grams. And this gives us a moisture content of 12%, which is important as it affects the soil strength. Okay, now this is the full raw data table used to plot the CBR graph. It records the penetration depth and the corresponding proving rings reading, which were later converted into loads value. This data is essential for plotting a precise graph and ensuring the accuracy of the CBR calculation. Okay, this is the graph that we get from the data table. This graph represents the load penetration curve obtained from the CBR test. As the penetration increases, the applied load also rises, which is typical for compacted soil behavior. So from this graph, we identified the load value of 2.5 millimeters and 5.0 millimeters penetration, which are essential for calculating the CBR value. These values are then compared with standard load values to determine the soil strength rating.
Discussions. For the question number 1, considering the average CBR values, explain whether the test soil is suitable for use as a subgrade, sub-base or base course material in road construction. How would you improve the soil properties if the CBR value are below the acceptable limits? So, the CBR test helps determine if soil is strong enough for road construction. The table shows a very low CBR value of 0.33%, while good substrate soil should have at least 4% CBR. This means the test soil is not suitable for use in road construction. To improve with soils, methods like adding gravel or sand, mechanical stabilizations, mixing with cement or lime, chemical stabilization, compacting the soil or improving drainage can be used to increase strength. So, for question number 2, explain how the CBR test results are applied in designing pavement thickness. Why is it important to perform both soaked and unsoaked tests for pavement material in real-world conditions? So, the answer is CBR value help engineers decide how thick the pavement should be. Lower CBR means thicker pavement is needed to support traffic locks. The soaked CBR test checks soil strength after being exposed to water, while the unsoaked test measures strength in dry conditions. Since roads often get wet, using only dry test result can be misleading. Performing both tests give a more accurate understanding of how the soil will behave in real conditions, ensuring stronger and more durable. In the conclusions, the CBR is essential in determining the appropriate pavement thickness, as soils with lower strength require thick layers to withstand traffic loads. By conducting both soaked and unsoaked tests, engineers can be better evaluate how soil behave in different moisture conditions, leading to stronger and longer lasting road design.